Hi, this video is to cover questions 10 through 14 on the test review. Number 10 asks you to describe the relationship between zeros and factors and to give an example. So recall that a polynomial is of the form f of x equals a to the x minus your first zero, your second zero, and so on. So the relationship shows if, for example, we had the function f of x equals 2 times the quantity x plus 2 times x minus 5, then we could say that by setting the factors equal to 0 and solving, we could get the actual 0 of the polynomial, meaning the x-intercept. So to describe the relationship here, we would state that the factors of a polynomial function can be set equal to 0 and solved for the variable to locate the roots or the x-intercepts on the graph of the polynomial function. So make sure when you are asked to write a written response that you do so in a way that uses the correct terminology and also is a complete sentence. The factors of a polynomial function can be set equal to 0 and solved for the variable to locate the roots or x-intercepts on the graph of the polynomial function. And here, this would be a good example. And of course, we could solve this one as well. So we know that our zeros, our x-intercepts or roots, are -2 and 5 for this function. Alright, next you're asked to describe the fundamental theorem of algebra in your own words. Your fundamental theorem of algebra actually talks about the number of potential complex roots of a function, but for all intents and purposes, it's okay to state that the fundamental theorem of algebra states that the degree of the function indicates, and that should be S, indicates the total number of roots, and I'll put up here real and complex, for the function. Fundamental theorem of algebra states that the degree of the function indicates the total number of roots, real and complex, for the function. Next, it says describe the remainder theorem and how it relates to long division. The remainder theorem says that if we were to do division, say we had a polynomial x minus a, and we divide it into some polynomial ax to the n plus ax to the n minus 1, meaning it's decreasing, that when we did this division, we would end up with a remainder. Let's say when we get done, we get a remainder of, we'll say b. So what it says is that if our remainder is b, then what we could have done was divide or evaluate the function at a to get b. So, and this is how it relates. If dividing by x minus a, f of a results in the remainder when dividing the polynomial by x minus a. Okay? So f of a, so we could say here that f of a would equal b, right? So if b was the remainder that we got, then when we evaluate f of a, we get b. And that's pretty much it. If dividing by x minus a, f of a equals b, well, let's see, let's see, if dividing by x minus a, f of a equals b, resulting in the remainder when dividing the polynomial by x minus a. Should be resulting there, sorry for that wording. All right, next, describe the factor theorem and how it relates to zeros. Give an example. So the factor theorem is directly related to the remainder theorem. The factor theorem says that if dividing a polynomial by x minus a, then x minus a is a factor of the polynomial if f of a equals 0. That's the factor theorem. If dividing a polynomial by x minus a is a factor of the polynomial if f of a equals 0. For example, if we were dividing some polynomial, let's see, x minus 2 and x plus 5, which results in x squared plus 3x minus 10. If we were to take x squared plus 3x minus 10 and divide it by the factor x minus 2, then we could also evaluate f of 2. Now that means when you plug in 2 here, you look for the resulting output. So 2 squared is 4, plus 3 times 2 is 6, 4 plus 6 is 10, 10 minus 10 would equal 0. So if we divide by x minus 2 and evaluate f of 2 and we get a value of 0, again, if we were dividing, that would be our remainder, then that means x minus 2 is a factor. X minus 2 is a factor because f of 2 equals 0. So it should relate to the two problems on the front of the page where you had to determine, let's see, right up here, evaluate the functions at the given value by division and explain what the solution tells you. So it lines up with 3 and 4. So factor theorem again, if dividing by a polynomial by x minus a, we know that x minus a is a factor if f of a is equal to 0. And again, that piggybacks off of the remainder theorem. For 14, it says to describe the complex conjugate theorem in your own words and give an example. Very concisely, the complex conjugate theorem states that all complex zeros of a polynomial function come in pairs. So, and further, if a plus bi is a 0 or root or x-intercept, or I shouldn't say x-intercept, it's not on the x-axis, then a minus bi is also a root. And I'm going to change that to root. I like root better. If a plus bi is a root, then a minus bi is also a root. So, for example, given f of x, if 2 minus 5i is a root, then 2 plus 5i is also a root. So notice, as much as possible, guys, use language that shows that you understand the vocabulary, that you understand the theorem, and that your examples reflect that you understand what the theorem is stating. Okay, so same here. I'm just not going to list 2 minus 5i and 2 plus 5i. I'm going to say given a function, if 2 minus 5i is a root, then 2 minus 5i is also a root. It does not mean, the complex conjugate theorem does not state that every complex number has a conjugate. The complex conjugate theorem deals directly with understanding complex zeros of a polynomial function and how they come in pairs. Okay? So please be careful about not using the word opposite. An opposite of a number is not a conjugate. So make sure you use conjugate to talk about 2 minus 5i and 2 plus 5i instead of opposite. Okay? Hope that helps. Good luck.